Okay, I wanted to take a second and do an example, and I'm going to do problem 1.5 because it's as good as any other one, but I want to make a video of this and just talk about some of these things here from 1.5. So here's 1.5 from the Numerical Methods book. It comes down to this. You have this differential equation, dv dt is equal to gravity minus c prime. Now notice this is, just to be clear, that's not the derivative, that's just a second c. This one is cd and this one's c prime, it's just another c, over m times v. Okay, so right off the bat, so we need to use MATLAB's symbolic algebra capability to analytically obtain the closed form analytical solution using this model for a case where the jumper is initially at rest. Okay, so what in the world does this mean? What does it mean to solve a differential equation? Let's just take 2 seconds to talk about that. Solving a differential equation simply means that for any time t, in this case, for this problem, to solve the differential equation, at any time t, I can tell you what the velocity is. That's what it means to solve a differential equation, right? So given that, let's go through and figure this out. So we want to use an analytical, the symbolic stuff. So what is the symbolic stuff? It's dsolve. So dsolve. And this is what this is how I do it. MATLAB squawks at you saying that it doesn't want to do this for very much longer, and I will change it when I have to. But right now, this is how I'm going to do it. So I'm going to say d, capital D tells it it's a derivative. V is equal to g minus c over m times v. That's it. So I want to solve the differential equation dv. Dv. This assumes it's dv dt. And which I'm going to go with. And now the initial condition is given right here in the problem, right? Oh, that was weird. That at v equals 0, t is equal to 0. Sorry, at t equals 0, v is equal to 0. So therefore, we're going to say, quote, v of 0 is equal to 0. And that's all you have to have. But because I want to do good form, I'm going to do this. I'm going to explicitly say solve this in terms of t. So that's not a huge deal, because you'll notice t is not on this side of the equation. But if, say, this was in terms of c or m or something like that, it would make a bigger difference. But solve this in terms of t. And then let's just run that. You're going to get an answer. There you go. That is the analytical solution. That is part A. Now I'm going to jump straight to part C, because, I don't know, it makes sense to me to do that. So I need to substitute in. Now I have g's and m's and c's, but I actually have values. They're given here for the values of those things, right? So I'm going to come in here and I'm going to say g is equal to 9.81, m is equal to 68.1, and c is equal to 11.5. Okay. So given that, I need to substitute those values into the other things. So let's do some stuff. Let's say f is equal to dsolve. I want to do subs of, I'm just going to replace f is equal to subs of f, sub into f. I want to substitute the values, boom, g, see, apparently, curly bracket, with the actual values of g, c, m. Let's run that, make sure it works, and there we go. So that is our equation. Kind of an awkward equation. Now you'll notice I did not substitute the values of time into this, and that's on purpose. It's not because I forgot. It's I don't want to do this. So what I want to do now is here it's going to say use a step size of 2 and continue the calculation out to 20 seconds. So we want to go from 0 to 20 seconds. So for part, this is part A and C. Okay. Later, I'm going to define in part B, I need to define h is equal to 2, the step size is 2, and time is equal to, I'm just going to call it t, is equal to from 0 in steps of h to 20. Okay. So given that, why do I do that? Is because now I need to turn around and I want to plot this thing. Well, this is just it's a function, but it's this, if you actually look at it, you'll notice that this is a symbolic thing. Right? It's a symbolic object. It's not a function. So how do we make it a function? That's where this MATLAB function bit comes in. So I'm going to say function is equal to MATLAB function of f. So let's run this, and I'm going to do what I forgot I'm going to clear everything every time I run it, just so we're working from a clean slate. So I took this, and I turned it into this. So if you actually look at the numbers, they're the exact same thing. So why in the world do I want not to have this, and I want to have this? Because I want to be able to do this. I want to be able to say plot t and function of t. So I want to be able to actually plot this up and calculate for every given t. I want to calculate what this equation would give you, and the way you do that is with a function. And so I run that, boom, and there's my plot. So, okay, so now that is part A, and then plotting part A. So now I'm going to do hold on. I personally like grid on and box on. Just makes I'll show you what it looks like. The grid turns on the grid, the box turns on these outer things. I don't know. This is what I like. Okay, so now that is part A. Now let's look at part B, the Euler's method. What is Euler's method? Okay, first off, let's talk about this for just a second. So what did we just do? We created an equation for the solution of this differential equation, right? So this differential equation is right there, and we solved it in the sense of we now have an equation. It's either f or fun, depending on which one you want to do, right? That is the closed form solution. So we can say that you can give an equation, y equals f of x type thing, right? So Euler's method is slightly different. Euler's method is saying, you know what? We're just going to calculate the value at every single point. So for every point t that we talk about, we're just going to turn around and calculate the value. So how do we do that? Sorry, this is part B. There we go. So to do this, we're going to do a loop, okay? And we're going to do loop from what to what. So we're going to go for I is equal to, 1 to length of t. Okay, it's actually going to be minus 1. I'll talk about why it's minus 1 in just a second. So what is Euler's method? Euler's method fundamentally is saying that the next value is the current value plus the current slope times the delta t. You're going to times the time step. So we're going to make this thing. We're going to call it v. V of I plus 1 is equal to so the next v is equal to v of I, the current v, plus the slope, so dv dt, times the step size. Not stop size, step size. And that is Euler's method. It's just that simple. So the thing is, we're missing a bunch of things. So let's fill it in. Okay. So first off, what is the first pass through this? I is going to equal 1, and so therefore v of 2 is equal to v of 1. But the problem is, well, v of 1 doesn't exist. But we should know what it should be. What should v1 be? V of 1 is equal to 0. Okay, so that's not v at time equals 1. This is the first element of the v vector. So what time does that correspond to? Well, it's going to correspond to the first element of the time vector, which is 0. So this right here is the same as this right here. Remember, this is symbolic. This is saying that v at time equals 0 is equal to 0. This is saying v, the first element of the v vector, is 0. And since this starts at 0, they're the same thing. Okay, so v of 1 is equal to 0. Step. I'm actually going to turn around. We call it h up here, so I'm just going to call that h right there, right? And then last one is the dv dt. So again, Euler's method. The next value is equal to the current value plus the slope at the current location times the step size. Okay. So what is a slope? Well, remember, what are we doing? We're solving a differential equation, but that differential equation is the slope. That's what this equation is. So let's do that. Let's say dv dt is equal to at, and we'll talk about this in a second, we'll put in something there, g minus c divided by m times v. Okay, that is what the slope is. Now g is constant, it's gravity, we've defined it up here, so we're good. C is a constant, it's right here, it's the drag constant. M is a constant, it's a mass, and so the only thing that comes into this equation is v. So this slope is only a function of the dependent variable of v. So dv dt is at v, this. Now, there's no reason why for this couldn't be, this differential equation maybe would be given as that, or maybe it would be given as that, in which case you'd have to send either t or t and v, you know, depending. But it doesn't matter. The point is given the differential equation, you just need the information that is necessary to calculate the slope where you're at. And for this problem, the only information you need is the velocity, or the, not the velocity, the v, maybe that, oh, that is a velocity, my bad. The v at that time. So now I have this function, dv dt, and I want to calculate it. So what, I need to pass this a function. So what do I need to pass it? Well, for this problem, I need the v at the current location. So what is my v at my current location? It is this right here. It's the v of I. So I just need to pass it. Whoa, yep, wrong button, sorry. So I just need to pass it that. Boom. And that is the Euler's method. And put a semicolon, please. Please, please put a semicolon on that one. And that's that. So we're going to run that. Boom. It's going to have that. It doesn't show up anything because we suppress everything. So now we actually want to add this to the plot, right? So to add that to the plot, I'm going to turn around and say plot t comma v. But here I want to do an r star dash dot. I don't know. I want to actually have, the key here is I want to have individual symbols, because this is fundamentally, you know, it's doing it a little bit different. So we're going to run that, and we have, there we go. Okay, so just for giggles, let's put on some x label is time in seconds. Y label is velocity in meters per second, given from here, right here, right? Title is Euler's method versus analytical solution. And legend, okay, the legend, the first one is the analytical solution. The second one is Euler's method. Just as to recall, what's up with this double quotes? Remember, when you're trying to do it in a string, if you do double quote, it'll do it as a single quote. Okay, boom, run that. Boom, Bob's your uncle. You got an answer. You're good to go. I don't like it there, so I'm gonna move it. There we go. Okay, there. That's it.